Hey, good morning everyone, and welcome to our webinar today on Hipot Testing 101. I am your presenter, Syed Abidi, one of the applications engineer here at Associated Research, and today I am live from Lake Forest, Illinois, and a very good morning to all those in the US, and a good evening and good afternoon to all those joining us from Europe or other countries. And thanks for being with us today. Um, Before we get into the main material of today's webinar, I'd like to go over some notes and also introduce you to our team. Well, first of all, myself, Syed Abidi, presenter today, and then we also have our other applications engineer, Bishan Patel, who will be assisting you on the Q&A chat line. So any questions during the webinar, if you have any questions on the material being presented, Bishan will be more than happy to assist you on the chat line. And then we have our organizer, Allison, today, who's also a marketing assistant, and she will be, organizing this webinar and assisting you with some of the things that we're going to talk about. So here's some notes on the webinar. As always, use the Q&A utility to ask us any questions concerning the material being presented. Again, this is where Bishan Patel will be assisting you in answering any questions that you have on the material that's being presented. If you run into difficulties, audio or video difficulties during the webinar, please feel free to ask Allison about them, and she would be more than happy to assist you on the chat line. You can also email Allison on the email address shown on the screen, allison.oba@arisafety.com, if you would like a copy of this presentation, and she's also available on the chat line. This webinar, like all our other webinars, is being recorded and will be available for view usually within a day or two on our website. So with that said, let's look at what was covered last time during our last webinar, which was electrical safety testing circuit theory. And in that webinar, which was presented by one of our other application engineer, Anthony Arroyo, he covered all the electrical safety test types, including the ground continuity, ground bond, the dielectric withstand test, the insulation resistance test, and the leakage current test. And then he talked about what part of the product is actually being tested, and then you guys also took a look at the actual circuits, the circuit representation of all these tests, how these tests are performed from a circuit point of view. And some other great features like arc detection and smart GFI circuits, safety circuits, were also discussed in that webinar. This webinar is focusing only on Hipot testing, and this is the first part of the Hipot testing webinar. That's why it's called Hipot Testing 101. We also have a Hipot Testing 102 coming up, and since Hipot testing is a very broad field, and there's a lot to talk about and learn about the Hipot test, we've decided to split this one into two different parts, and we will cover some of the basics of Hipot testing today, and then in the next webinar, which is Hipot Testing 102, we will talk about some other details and some other special cases of Hipot tests. So with that said, let's look at our learning objectives for today, and at the end of today's webinar, hopefully all of us will be pretty familiar with with the Hipot test itself. What is the Hipot test? What is really being tested during the Hipot test? We're also going to look at some of the test requirements and parameters relating to how the test standards call out Hipot testing requirements. And then lastly, we're also going to look at some Hipot test considerations and failures. We're going to try and understand and differentiate between different types of Hipot testing failures. And we're going to look into arc detection a little bit more in detail. We will also have a few videos for you. I'll play a few videos showing different types of Hipot test failures, and we will also have a couple of poll questions for you, which we highly encourage that you participate in those. It gives us great information and to us in terms of improving our products and the material that we're presenting. So with that said, let's dive into the main material of this webinar. So the Hipot test, it is very important to first understand what the Hipot test is all about and what it's testing, what is really being tested, and why is it required. So first of all, the dielectric voltage withstand test is the technical name or the more common name that's used by most of the test standards. The Hipot is short for high potential, and again, that's also a very commonly used term for this test. So basically, you can use dielectric withstand voltage test or voltage withstand test, Hipot test, and some people, I think in Europe, also like to refer to it as a flash test. So the Hipot test is one of the most common types of electrical safety tests, meaning that if you look at the test standards, you will notice that most test standards call out for Hipot tests to be performed on different electrical products. So this is, in almost all standards or electrical safety test standards, Hipot test is most likely going to be called out for. So what does this test do? Well, first of all, every electrical product has some sort of insulation, different insulation barriers that are separating your current carrying conductors versus non-current carrying conductors. So this test is it's designed to verify that the insulation of an electrical product is adequate enough to withstand a high voltage condition. So this test is performed by stressing that insulation of the product far beyond what it would encounter during normal use. Meaning that, for example, in the US, a product is, powered up using the wall outlet, which is around 120 volts, 60 hertz. So the Hipot test will stress the product's insulation to at a much higher level of voltage and record the resulting leakage current or look for breakdowns. And these are some of the things that we're going to talk about in more detail. So the term voltage withstand test comes from the fact that it is a test to see if the insulation of your product can withstand the high voltage condition for a given amount of time without breaking down. Let's look at, and I know we've looked at this circuit before, but again, since we're talking about the Hipot test, it's also important to look at it from a circuit point of view and really see what is going on during a Hipot test. How does the product that is undergoing a Hipot test look like? So the diagram at the bottom of the screen shows the basic circuit for a Hipot test. On the right side, you can consider that as the product under test or the device under test, and on the left side is our Hipot tester. So we learned that Hipot test is a deliberate application of high voltage potential between the current carrying conductors and any exposed dead metal or chassis or ground. The resulting leakage current is measured to determine whether product insulation is able to withstand this high voltage without breaking down. And this test verifies that the insulation of your product is capable of protecting the user from any leakage currents as a result of an electrical fault within the product. Now, all electrical products have some sort of insulation, insulation between different points in your product, and insulation that protects any human from touching if a human being comes in contact with the chassis of the product, and if it's powered up, it is the insulation that's protecting the user from getting any electrical shock if there is a higher amount of leakage current flowing on that product. So leakage current is always present in almost all electrical products, but it does become a problem when it reaches higher values. Obviously, we don't want to come in contact with any high current values. So looking at the circuit, when a high potential is applied, let's consider an example of a three-prong line cord for a product that has a ground circuit as well, so a class 1 product. The way a Hipot test can be looked at is that the high potential is applied by shorting the current carrying conductors of this product, meaning in this case it's going to be the line and neutral, or the hot and neutral, and the voltage is applied between those current carrying conductors, and the lower side of that voltage, which is the return connection, is tied to the ground or the chassis of the product, which in turn, if you think about a product undergoing Hipot testing, you can almost think of that product as a giant capacitor, because what is a capacitor essentially? It's a it's basically a insulator or a conductor, two conductors separated by an insulator. So here's what's going on in the Hipot test as well. If you look at the product, you're applying the high voltage between two conductors, and it's the insulation in between those conductors that's being stressed, and it's being tested to see how long can it withstand this high voltage or over voltage condition without breaking down, or how much leakage current is going to flow as a result, which gives us a great understanding of the quality of the insulation of our product. And from there on, we can see if the insulation does not meet the standard. We can, manufacturers can go back and improve upon their product. And it is the leakage current in the end that gives a measure of the product's insulation quality. And we will look at some test parameters, and we'll get a better idea of what those parameters mean, how they can be used to detect failures in the Hipot test or during a Hipot test. So here's a condition showing the a Hipot test that has passed, meaning that a high potential was applied between the current carrying conductors and the non-current carrying conductors, and the insulation of the product was good enough to not allow high amounts of leakage current flowing on the chassis of the product. And the end result of the Hipot test is a pass condition. So in this case, the insulation is able to withstand the high voltage and does not break down, or does not allow excess leakage current to flow on the surface of the product under test. So what's important to remember is that good quality insulation will not allow, or should not allow, higher amounts of leakage current to flow on a product's surface. If the insulation is poor quality, or it's degraded, because over time any electronic product with more use, the insulation of that product will degrade, and that's why it is important to keep a check of the insulation of your product. The next picture we're looking at right now is showing a Hipot fail condition. So what may have happened here? Well, a couple of things may have happened here. Same high potential was applied between the current carrying conductors and the non-current carrying conductors. The same insulation was stressed. However, in this case, the result is a fail, meaning our Hipot test failed. Why? Because in this case, the insulation of the product could not prevent higher amounts of current flowing to the chassis of the product. And in other words, the insulation experience a breakdown condition, which results in excessive leakage to the chassis of the device under test. So poor insulation will definitely break down and allow dangerous leakage currents to flow on the surface of a product, making the product unsafe to be used, because it can pose a safety condition. So the Hipot test is a very versatile test in that it can, first of all, it's testing or stressing the insulation of our electronic products to see how good the insulation is, how good the quality of this insulation is. But the Hipot test is a versatile test in that it is not just used for testing the insulation, but it gives the manufacturers of different types of products a really good idea of the overall quality of the product. Um, and I know we've talked about type tests in one of our previous webinars and versus production line tests, but just for a quick overview, because I'm gonna mention these two tests, going forward. Type tests are tests that are performed during the design phase of a product versus production line tests that are performed on fully manufactured devices at the end of production line to ensure that the fully assembled product is safe for the user, for the end user. So Hipot test is mostly required as a type test as well as a production line test. However, the parameters may vary depending on the standard you're trying to comply with, but when performed as a type test, meaning during the design phase in a lab environment, the Hipot tests are helpful in finding various important defects such as nicked or crushed insulation, stray wire strands or braided shielding, conductive or corrosive contaminants around the conductor, spacing problems between terminal and tolerance errors in cables, inadequate creepage and clearance distances between current carrying conductors on a circuit board or in a product during the manufacturing process, because it is during the design phase where type tests, Hipot test is considered as a type test and is performed to make sure that it is your product that you're designing is meeting the standards that you're trying to comply to. Now, the Hipot test, like I said, is also performed as a production line test. Again, that's when the fully manufactured product is ready to be shipped out in the market. A production line Hipot test is performed with slightly different parameters, again based on the standards. But during the production line Hipot test, it gives us some really good information, and it determines whether the construction of a product or a unit is about the same as the construction of the product that was subjected to type testing. So basically, again, the reason we have a production line Hipot test versus a type Hipot test is because, first of all, during the design phase, the type Hipot test gives the user good information on the design of the product, and in the end, on a fully manufactured product, a production line Hipot test gives us a good understanding of whether this fully assembled product will be safe for the end user to touch and use as normal. Some of the process failures can be detected by a production line Hipot test. For example, maybe a transformer wound in a way that a creepage and clearances have been reduced. Again, obviously the same product, the same design of the product has been through a type Hipot test, but during manufacturing things can go wrong. There could be defects, there could be operator errors in putting different types of spacing between conductors and whatnot. So this is where the end-of-line production line Hipot test comes in very handy to ensure that the manufacturers are shipping products out that are safe to be used. Such failures can result from new operators working in the production department. So again, a very good test, a very important test to perform on products. And the Hipot test is more than just a go-no-go test. So basically it can be used for detecting many different problems during design as well as on fully manufactured products. Here's some examples of the kind of things the Hipot test can detect: scrapes, pinholes, spacing, crimps, heat material buildup, moisture, and like I said earlier, the insulation of any electrical device can break down or become weak over time. So it is very important to ensure that the quality of the insulation of our product is in good shape. With that said, I'd like to quickly show you guys video of a Hipot test being performed using one of our 500 VA testers. As you can see in this picture, I'm going to pause it right here because I want to talk about the settings a little bit. And like I said, we're going to talk about some Hipot test parameters later in this presentation. But right now what we're looking at is a Hipot tester which is set to output 1.24 kV or 1240 volts, and with a high limit set at 10 milliamps, and the test is will be run for 1 second. The load or the product under test in this video or in this case is one of our verification boxes, which is nothing but a load bank or resistor bank, with different combinations of resistors to come up with different resistance values. And once the output on the Hipot tester is enabled, you will see that the Hipot tester starts to record some leakage current which will be displayed in the milliamps. The high voltage side of this Hipot tester will be connected to one end of the load, and the return side connected on the other end. So you can see we're trying to verify that this Hipot tester works, and it's able to catch failures and passes. So here's the connection, and once we hit the test button, you'll see that 1.24 kilovolts of potential is applied, and the resulting leakage current is 0.62 milliamps. Now this leakage current is a result of the high potential, the 1.24 kV that was applied across the load, that resulted in a leakage current of 0.62 milliamps. In this case, since our high limit was set to 10 milliamps, it resulted in a pass. Accordingly, once the user has a good idea of what the high limit should be and the low limit should be, most Hipot testers allow users to set those limits to catch, failures, Hipot test failures. So let's look at a few more, things that are important to know about the Hipot test, such as, so the best indication of a dielectric breakdown is a leakage current measurement significantly higher than the normal or the nominal leakage current measurement. This means that, so first of all, breakdown is one of the failure types that is, that's why the Hipot test is used on products to detect breakdown conditions, to detect shorts, to detect if it's leaking dangerous amounts of current. The test voltage and the product being tested and the capacitance of the product can all impact the total leakage current measurement, meaning that if a product is highly capacitive, there may be other things to consider, because it may leak a higher amount of current than a product compared to a product that is not highly capacitive. So all these factors do influence the result of the Hipot test. When the Hipot test is performed on a product, again, we can think of it as a giant capacitor, and then the higher the capacitance of a product, the more leakage current will be seen as a result. And based on that, the ideal or the appropriate Hipot tester should be selected. For example, if you know your product is very leaky and you are expecting very high leakage, you may want to use a 500 VA Hipot tester to ensure that you have enough leakage current. But Associated Research has a few 500 VA models that can measure and output up to 100 milliamps of leakage current. So for products that are leaky, a 500 VA or 100 milliamp Hipot tester would be a better solution. So again, the voltage during a Hipot test, the high voltage is applied between the mains input and the chassis of the product. Now this is just one case of a Hipot test. There may be, there are different types of Hipot tests depending on the type of product being tested. For example, in some of the medical devices, there are Hipot tests. There's your basic Hipot test from mains to your chassis point or the ground point. Then there may be a Hipot test from mains to some of the applied parts or different points on the device, which is basically what it's doing is it's testing, or we are testing different insulation barriers in our product. So we have one insulation barrier between our current carrying conductors, which is our line and neutral and ground, and there are other insulation barriers as well, like your applied parts, your enclosure, and those all need to be tested. And you'll look at some of those examples as we move forward. Um, let's look at some of the test parameters to consider for the Hipot test, because there's basically a rule of thumb for setting the Hipot voltage. However, sometimes, in some cases, the standards will call out for a voltage value that needs to be used for the Hipot test. But unless and otherwise stated by the safety standard, a good rule of thumb to calculate the Hipot test voltage is you take the nominal voltage and multiply that by a factor of 2, and you add 1,000 volts to it. So for example, the Hipot test voltage for a product that has a normal operating voltage of 120 volts will be twice of that, which is 240 plus 1,000, so the 1240 volts or 1.24 kV number. Again, this is the rule of thumb. However, these numbers may change depending on the standard and the type of products that that are undergoing the Hipot tests. So in some cases, safety agencies require for a Hipot test, for a different voltage for performing the Hipot test. For example, medical devices. This one's a good example because we're going to show you some pictures going forward of a medical device undergoing Hipot tests. And if you read the 60601-1 standard, which is a big standard for the medical devices, you will see that in some cases for some special types of medical devices that have a direct contact with the patient, those points, which are commonly referred to as patient connections or applied parts, those are required to be tested at 4,000 volts. Now, again, this is a much higher number. If you do the rule of thumb, we calculated about 1.24 kV for a device rated at 120 volts. Whereas in this case, for an applied part connection, the test voltage is specified by the standard. So we have to use 4 kV to test that insulation barrier between those points that touch the patient and returning back on the mains conductors or ground of that medical device. We also talked about Class 1 products versus Class 2 products in some of our previous webinars, but just to do a quick recap, Class 1 products are products that incorporate a grounding circuit, a safety ground circuit. Meaning a good example would be any product that has a 3-prong line cord, with the third pin being the ground pin that is connected directly to the chassis of the product. Now, Class 1 products do have insulation as well. That's why Hipot test is required to be performed on Class 1 products. Class 2 products are, they don't incorporate a safety ground circuit, but they do have, a reinforced insulation or double insulation barrier, which is basically the only, barrier protecting the user from coming in contact with leakage current. So most double insulated Class 2 products are subjected to design tests at voltage levels much higher than the rule of thumb described above. And why is that? Because Class 2 products, they don't incorporate a ground. However, they have a reinforced insulation. And since the insulation is reinforced and that's the only protective barrier between the user and leakage current, that insulation on a Class 2 product may be subject to much higher voltages, so the rule of thumb may not apply in those cases. However, always it is the test standards that call out for setting up the test parameters for the Hipot test, and that the test standard should be our main reference guide when setting up the Hipot test and all the test parameters as well as failure settings. So we were just talking about class 1 versus class 2 application. Now, like I said, Hipot test is required for both class 1 and class 2 products because there is an insulation barrier in both. One has dual insulation or reinforced, one has just a single layer of insulation along with the ground. So in this picture that we're looking at, we're showing a product, you can consider this a medical device, being are undergoing an AC withstand test. Now the high potential, which is the red cable coming out from the Hipot tester on the left, is connected to, if you look carefully, it's connected to the line and neutral, the hot and neutral conductors on the line cord of this product under test. And the return cable is connected on the chassis of the product. That's just one example. This is a class 1 product. Now, same product, if we were to assume that this is a class 2 product, well, since it doesn't have a grounding connection or a chassis or a conductive chassis point where we can measure our leakage current, sometimes the standards will call out for creating a conductive contact by wrapping a piece of aluminum foil around the plastic chassis of a product, because since it's a class 2 product, it doesn't have a grounding point. We have to create a point or on the chassis of this product which is conductive to be able to measure some leakage current, and this is how the standards call out for doing this, wrapping a piece of foil on a point that the manufacturers think is appropriate, and connecting the return connection to that point, which gives which allows a conductive contact to be made and some leakage current measurements to be made by the Hipot tester. And in this case, as you can see, the return is connected. It should be touching on that conductive contact. Another example of a class 1 application versus a class 2 application. In this case, some of associated research models, Hipot test models, instead of using exposed leads and clipping leads, we have adapter boxes that can connect directly to the Hipot tester, allowing for a safe connection where the line cord of the device under test can be plugged into the adapter box in a safe manner without any exposed conductors, and the return connection is connected on the chassis of the product. This allows for a safe method of performing Hipot test. And the shorting of the line neutral is achieved by the adapter box instead of us trying to tie a piece of wire between line and neutral and making an unsafe test environment. Similarly, for for products that are undergoing different types of tests, Associated Research has a full safety compliance analyzers such as the Omnia 2 models that can allow a Hipot test to be performed using different methods, connection methods, or different techniques. If you're just running a Hipot test, the connections may be different, but if you're running a full gamut of electrical safety tests from continuity, ground bond, insulation resistance, and leakage current tests, the connections may vary a little bit. And for those who for those of you who are already using the Omnia, leakage current testers that also incorporate all other test types, will know what I'm talking about here in terms of different types of connections that can be made to perform the Hipot test. So that leads us to look at some examples and examples right out of the standards, how the standards are calling out for these dielectric withstand tests. and how they want users to perform these tests on their, or manufacturers to perform these tests on their products, depending on their product type and what category their product falls under. Um, there's like I said in the beginning of the webinar, this is just the 101 part of the Hipot testing. There's obviously a lot more to consider and learn about the Hipot test, such as, you know, the difference between AC and DC Hipot test, the 500 VA Hipot test, the hot Hipot test. So some of those things will be covered in the upcoming webinar. That's why we encourage you guys to follow us, because, you know, we build upon, each webinar is building upon the previous one. So if you follow the full series, you will, you know, you will be able to follow what we're trying to achieve with these webinars. So looking at an example here from UL 1598, this is the, I believe, the standard for luminaries, LEDs, lighting industry. If you look at the requirement for the dielectric voltage withstand test, the test voltage is called out for 1000 volts AC for incandescent luminaries, and the test voltage is called out for 1000 plus twice the rated voltage, which is the rule of thumb that we learned earlier. And for all other luminaries, test time is also called out for 60 seconds. And the pass criteria, now this is important because you know, the standards may be calling out for different criteria, and, you know, there may, you as a manufacturer, you may have a slightly tighter or stricter requirement for pass criteria, and that's where you start using the high and low limits and, you know, or trip conditions in the Hipot tester to detect failures. So in this case, the pass criteria is called out as no breakdown on the product's insulation shell occur. This means if you're trying to comply with this standard, you're just looking for breakdowns. To comply with the standard, you just want to make sure that the insulation of your product does not break down as a result of the high potential applied across its you know, current carrying conductors and non-current carrying conductors. If the, again, the important point here is to see how it's calling out for non-conductive material. If DUT enclosure is non-conductive, use metal foil as conductive medium for return point. Again, like, you know, we already talked about this, and I just want to emphasize on the fact that all this information that we're giving you about the Hipot test is derived directly from the standards. So the standard is what we reference to all the time to learn about different requirements on different types of Hipot testers. Now this was for a type test. And under the same standard, if you look at the factory production tests, the Hipot test is called out for 1200 volts AC between primary circuit and accessible dead metal chassis, and the time, as you can see, is reduced. And this is why I talked about the difference in test parameters for Hipot tests, between a type test and a production line test, because type tests are usually more stringent and more strict, whereas production line tests are tests because they're performed because the type test can determine some issues during the design phase, but the production line tests are your end-of-line tests. So before a product is shipped out to the user, you want to make sure as a manufacturer that your product is safe to use. And again, looking at the example, the test time has been reduced for a production line test to 1 second. There's also a requirement for a ground continuity test. Again, this is only applies for Class 1 products that have a ground circuit, or a ground bond test where it may ask you to, pump 30 amps between the earthing contact point and accessible conductive parts, and then measure the resulting impedance of the ground circuit. So that's again getting to the ground bond test. But like I said, in some standards, call out for Hipot tests as type tests as well as production line tests, and and then they can add more types of tests to go along with the Hipot test. And ground continuity and ground bond tests are something that we've discussed in the previous webinars. However, we have one full webinar dedicated to the ground bond and ground continuity test. So keep following us and we will educate you on all the electrical safety test types. Another example from the big medical standard that I was mentioning earlier, the IEC or UL 60601-1. In this case, if you look at the test voltage, it's referring you to a table 6 and 7, and the table will call out for different test voltages or give you an idea of how to calculate those test voltages depending on the type of medical product, because medical devices and medical products or machinery can have many different connections, outputs, and depending on what those outputs are doing, how they're coming in contact with the patient, that would determine the type of connection that is. And again, this reference chart in the standard will give you an idea of what would be the appropriate or the ideal voltage to to use for testing those different points on the product. The test time in this case is called out for 10-second ramp up, 60-second dwell, 10-second ramp down, tested at 50 hertz, 60 hertz, or this is interesting here because it's saying that it's you'd either use the AC Hipot test or the equivalent DC Hipot test, meaning if you multiply the AC Hipot test voltage by a factor of 1.414 or square root of 2, in other words, you can use that value of voltage as a DC voltage to perform the Hipot test. Again, the pass criteria: no dielectric breakdown. If the DUT enclosure is non-conductive, use a metal foil to form a conductive medium. So all this information that we looked at in terms of looking at the standards, test standards, we can see that the production Hipot test parameters, can differ from the type test parameters, but in the end, they're both Hipot tests and they're testing the same insulation points or insulation barriers on your product. Another quick example of 60335 test standard, this is actually calling out for a 500 VA test under the type test. So again, like I said, some standards may call out for a 500 VA test, and 500 VA test, a Hipot tester, is just a more powerful Hipot tester that is, that can output. In our case, our maximum output current or leakage current measurement is limited to 100 milliamps, so that's a pretty high amount of leakage current. Usually, commonly, most products don't go that high up, but again, in this case, since the standard is calling out for it, there may be a need for using a 500 VA tester. And like I said, we'll talk more about 500 VA requirements in the next part of this webinar, Hipot 102. And then, there's different test requirements as well. There's no breakdown on a product's insulation. However, what I do want to emphasize here is that even though the standards may be calling out for no breakdown, which is great, which most of products will pass, but from being in this industry and from our experience, we have seen that our manufacturers really like to utilize the high and low limit settings of the trip current, of the leakage current, and that requirement may come in from a quality point of view. Well, obviously, most of our, as a manufacturer, if I'm a medical device manufacturer, for example, my products, all of my products, may be passing the Hipot tests with no breakdowns, but from my own quality perspective, I would want to put in a high limit and a low limit to see if the results of my Hipot test performed on different samples of products that I'm manufacturing are consistent. I want to make sure, from a quality assurance point of view, that all my products are exhibiting the same amount of leakage current. So from that perspective, I can utilize the high and the low limits and different other types of failure detectors in my Hipot tester to ensure that there's consistency between products of the same type that I'm manufacturing. With that said, it's time for our first poll question. I know we're running a little short of time, but the poll is open right now, and the poll question is displayed on the screen. Please participate in this. Take a minute to participate, and we will be back after a brief pause.
Hi everybody, thank you so much for participating in our first poll question of the day. If you are required to perform both a type test and a production line test, I'm going to go ahead and close the poll question. 42% of you are only performing production line Hipot tests, 19% of you only perform type Hipot tests, 35% of you perform both type and production line Hipot tests, and 3% of you don't currently perform either. Thank you guys so much for participating.
Thank you, Allison. Thank you. Thank you to everyone who participated in this poll question, and the results are not surprising. So a lot of you are performing production line Hipot tests. Some of you are performing type Hipot tests as well, and about 35% of you are performing both. And for those who are not performing a Hipot test, I guess you are here to learn about the Hipot test, because at some point going forward you may be needing to perform a Hipot test or deal with electrical safety testing. So that's great to know. With that said, I am going to play a quick video to show some of the failure types. And before I go into that, I just want to mention, there's different failure types such as breakdown. It could be, if you're using the high and low limits, there could be high and low limit failures. And there could be arc detection failure or arcing failures as well. And I'm going to talk about arc detection briefly as well. But let's look at a breakdown failure condition. So what's going on here is the test is set for 5,000 volts, and here's the red lead is the high voltage lead, the black lead is the return lead. As you can see, they're spaced very close together, and as the voltage ramps up to up to 2.3 kV. Let me play that again because that was a short video. So the settings here are 5,000 volts output for 5 seconds with some ramp up time, and the high limit is set to 50 milliamps, meaning that this, if the leakage current measurement in this, in this test exceeds 50, it should result in a failure. But the test is set up to catch breakdown condition, and breakdown is basically, high amounts of discharge of leakage current. The insulation of a product breaks down and allows very high amounts of leakage current to flow on the chassis of the product. And in this case, we have created a breakdown condition by placing the high voltage lead or cable tip very close to the the other side of the circuit, which is a return lead. So in order to create a breakdown condition, and that, as you can see, as the voltage ramps up from 0 to 5,000, somewhere around the 2.4 kV mark, it's enough potential difference between the high voltage and return to cause a breakdown condition. And this is that's what's basically going on in this video. I'd like to show you another video with a high limit failure, and in this case, again, we have a 5,000 volts test set up, and in this case, the product being tested, the yellow box we saw is a capacitor. So and as you can see, because it's a capacitor, the nature of capacitor is such that it will pull a lot of, let me play that again, a lot of current, and that can result in a high limit failure. So even though the high limit is set to 50 milliamps, you can see right here that the current exceeded the 50 milliamp, and the reason this failure was caught in this Hipot test instrument is because there was a high limit set which was crossed, and uh, it resulted in a high limit failure for your Hipot test. And as you can see, the full voltage potential did not even reach the 5 kV that was programmed. Similarly, we have a failure, test, same test parameters, but this time we're looking for shorts, and that's one of the big things that the Hipot test is performed for, is to look for shorts between your current carrying conductors and the non-current carrying conductors. So let's take a look at this. What we did here was we basically shorted the high voltage directly to the return circuit to see if it can catch a short condition. As you can see, the failure resulted in a short. So if, in other words, if there was a device under test connected to this Hipot tester and it had an actual short, this test should be able to catch that condition and give user some good information. All right, so let's continue with our material. I know we are running a little short on time, but we'll try to get through these fast. So we just looked at some of these failures in our videos. So starting with a breakdown failure, the first video we saw was a breakdown failure, meaning that very high amounts of leakage current was detected and instantly, and that resulted in a breakdown condition. Now this is different from a shorting condition where it's a direct short between your current carrying conductors and your chassis. So the Hipot testers that Associated Research makes are able to differentiate between a shorting condition and a breakdown condition, and these are fast interrupts, and they will cut the voltage output down and end the test in a very short amount of time, around the 400 microsecond interrupt mark. Again, the other video that we looked at was a high limit failure. Like I said, most of the Hipot testers these days allow the users to program a high and a low current limit thresholds to catch failures, and these are slightly slower than the breakdown and the shorting conditions, obviously due to the nature, because the voltage at sometimes is applied gradually, ramped up, and once it reaches the full peak, it may result in a failure later on. So the 100 millisecond samples are taken by our Hipot tester, Associated Research Hipot testers, and displayed on the screen every 100 milliseconds. The third thing here is an extra feature that some of our Hipot testers have incorporated, and that's called the arc detection, or the arc failure. Now, each failure detector has a priority on the instrument. Shorts and breakdowns will always be detected with highest speed interrupts. Leakage limits will trigger a failure if leakage current strays from the programmed values. Arc detection is the extra feature which can be enabled or disabled. And in order to understand arc detection, it is first very important to understand what is arcing. Well, arcing is commonly defined as a momentary partial discharge of a partial discharge due to the intense electric field or concentration of intense electric field across a insulation of a product, or in other words, dielectric. And in the case of Hipot testing, the dielectric is usually referred to as the insulation of a product. And in many cases, arcing conditions can be seen as a luminous discharge caused by the ionization of air molecules, and that's why it can actually be in a dark room. If there's arcing going on during a Hipot test, you can actually see that arcing because you will see a discharge for that reason, and those in other words, that's called the corona effect. And what's going on is that high impedance arcing is it's a temporary condition. It's not it's not necessarily considered a sign of breakdown, because again, we know what is a breakdown. So arcing is not considered a sign of breakdown. If you are using arc detection in your Hipot testing, and if the test resulted in an arcing failure or arc detection failure, that does not mean that the insulation of your product is is in a very bad state or it's breaking down. Arc detection will give you a good idea, or give manufacturers a good idea that or it may be looked at as a sign that the insulation may not be in the best shape, and it may break down going forward or in the near future. So it's more of a quality check. So do not confuse arc detection with your breakdowns or high limit failures. Now, how is arc detected on at least in terms of associated research Hipot testers that incorporate an arcing failure? How is arc detected? Well, first of all, there's arcing are high impedance arcs and coronas that generate high frequency current pulses that ride on the low frequency input waveform. The way arc detection works in associated research models is that those signals are fed through a high-pass filter. So those high-frequency arcs are filtered from the low-frequency input waveform, and the user is able to program the sensitivity level of the arc detection in our instruments. And once those high frequency signals are filtered, they're compared against the user defined sensitivity level, which is from 1 to 9. And what happens is that then the comparator compares those two values and sees that if the user is very tight, if user is very about setting up the sensitivity level, the arc detection may trip at a higher sensitivity. Whereas if you're not too worried about arc detection, you can either have this feature off, or you can set a sensitivity level that is not that sensitive, it's less sensitive. And then those are fed to the processor of the Hipot tester, and that determines if a arcing failure has occurred or not. Here are some of the approximations of the settings that I was talking about from 1 to 9, with 9 being the least, the most sensitive, referring to almost or approximately a 2 milliamp trip level. What's important to know about arc detection is that there are no real standards that are that define arc detection, and they call out for actually testing for arc detection or looking for arcing. And arc detection is not an exact science. There are many variables involved, including surface geometry, altitude, atmospheric pressure, other environmental conditions, that can affect arc detection, and it's a very sensitive circuit and reading. So with so many variables, arc detection becomes more of an approximation than a science. And in the end, it is ultimately up to the manufacturer to determine whether or not to use arc detection, and if so, at what sensitivity level. Again, I want to emphasize on the point that we talked about arc detection, but we want to make sure that you're not confusing arc detection with breakdown, short failures, or high limit failures. This is a completely different circuit that more of a quality check, in our opinion, for manufacturers who are very strict, and they want to make sure that they can predict. Basically, arc detection can be used to predict how well the insulation is going to last, in the future, in the near future. That leads us to our second poll question. Again, I apologize for being running out of time here, but these things are important to learn, so I'd highly appreciate if you can participate in this poll, our second poll of the day.
Hello all. Thank you all again for participating in our second poll question of the day. We asked, when a product fails a Hipot test, what is your organization's protocol? I'm going to go ahead and close the poll question. As you can see, 36% of you say that you retest the product. 50% of you say you set the failed product aside for further testing, which I would say those two options would probably be your best options for when a Hipot test fails. 11% of you say that you change the test limits, and then 4% of you say you discard the product. Syed, I think it might be helpful for everyone to understand why changing the test limits on their DUT may not be the best option. Thank you all again for
Sure.
participating.
All right, thank you, Allison, for giving us this good information, and thank you all for participating in this poll. And I'm glad to hear that most of you know exactly what to do when you encounter a Hipot test failure, and not just change the test limits, because that won't resolve issues for your testing. Because you can basically, changing the test limits is the same thing as you're trying to basically force the Hipot test to pass, and that may not be a correct Hipot test to perform, just by changing the limits and making sure the product is passing. When you have set a criteria, a pass-fail criteria for your product, for your Hipot test results, you want to make sure that all your products are consistent with those results, and the leakage limits should not be changed. Whereas when a product fails a Hipot test, it's the best idea is to either retest or put it aside for inspection to see why did this particular sample product fail compared to the other ones, because it's essentially the same design, same kind of product, same insulation. Why did this fail? Well, there could be many different reasons, which we have already talked about, such as the product may have encountered something during the manufacturing process or the production process. Somebody may have made a mistake, or operator error, or some kind of error that may have change the original design in terms of how the insulation of the product is. Spacing may have been different. Many different things could have happened during the production process, and that's why the end-of-line production Hipot test is very important, because it allows you to determine if a good product is being shipped out or not. But going back to the poll question again, the selection that says change test limits is something we just put in there, but that really should not be your choice of action upon seeing a Hipot test failure. A failure is an indication of bad insulation or some other issues in your product. So as as responsible manufacturers, we should always retest the product and look into a failed product and fix the issues and retest it again, instead of just changing limits and passing the product. That can lead to really bad things. If a product that was not properly Hipot tested reaches the hands of the end user and something happens, or some electrical accident occurs and the user gets shot, the manufacturer can be in a lot of trouble, legal trouble as well as financial trouble. So that sort of leads us to the end of our webinar, and before I sign off, I want to make sure that you guys have all the information that you need. Again, if you need a copy of this presentation now, please email Allison at allison.oba@arisafety.com. Please use our website for more information, which is arisafety.com. Follow us on social media, LinkedIn, YouTube, and also on Twitter as well. And I know we've run out of time here, but I will be open to any last-minute questions. If you guys have anything that you feel I should answer to everyone, please put those on the chat line, and Bishan will be happy to announce them, and I'll try to answer them to the best of our ability. If not, email us with any list of questions you have, and one of us will reach out. We have a great support team here.
While we're waiting for potential questions, Syed, you were going through the standards guide quite a bit, so I placed a link to the standards guide in the chat box for anybody who's interested in learning more about their standard and any product that might be a best fit for them. So feel free to click on that.
Great, thanks, Allison, for announcing that. Yes, we did go quite a bit into looking at the examples from the actual test standards, and again, those are the guidelines of this safety industry. It's the test standards that are guiding the electrical safety industry, because every manufacturer is trying to comply with those standards in the end to pass audits. And I know auditors can give manufacturers a hell of a time, so we want to make sure we are performing the tests according to the standards and keeping our auditors happy, which is, I know in some cases, a very difficult thing to do. So yeah, go ahead.
Syed, we have a question. How often should I recalibrate my Hipot tester?
Sure. So the question is, how often should you be recalibrating or calibrating your Hipot tester? Well, as a manufacturer of Hipot test equipment and electrical safety test equipment, Associated Research recommends a yearly calibration to ensure that your instrument is, all the data points on your instrument are within tolerance limits and it's meeting the specifications that we call out for. So yearly is what we recommend, but from experience and dealing with different customers, we have seen some customers are using a 6-monthly or even a 3-monthly quarterly calibration. It really depends on how the test environment is. If it's a very rough environment, you may lose calibration. Also, depending on the frequency of use, if it's a very, very high frequency usage, you may want to check for calibration more often than once a year. So again, as a manufacturer, we recommend yearly, but if you guys feel, depending on the nature of use and the condition it's being used in, the Hipot tester, you can definitely go for a 6-monthly calibration or even less. It's really up to the user in the end. While we're looking at some more questions on the chat line, I would also like to inform you that we have a series of webinars, which are covering different topics. So I would highly recommend you guys, those who have missed the previous ones, they're archived on our website and they're there and available for you to view, and keep up with our 2016 series of webinars, which will contain lots of good information on different test types, and overall it's a great platform to educate our clients, and not just our clients, anyone who's interested in learning about electrical safety testing is more than welcome to join our webinars, because again, in the end, we are part of the safety industry, and we want to educate people about these things as well.
Side, real quick, there's I know this is a common question that we get about setting the high limits and low limits. This was asked earlier, so if you could quickly, there's still I think 33 people here, so if you could go over how we get the high limits set, and also maybe what the importance of low limits are.
Sure. So like I said, this webinar is split into two parts, and we had decided to talk more about setting trip limits in the next part, but I'd be more than happy to briefly discuss how the current high and low limits in a Hipot tester can be set. So for example, the way we usually recommend our customers is to take, for example, 10 samples or a number of samples of a product and perform a Hipot test on those products. Note down the leakage current values for those 10 samples, then average them out. For example, out of 10 samples, you're getting an average current reading of 2 milliamps as an average number out of the 10 samples you've tested. Based on this number, the average number, you should be able to set a high limit and a low limit, because now you know that on average my product or this particular type of product that I'm testing is exhibiting 2 milliamps of leakage. Now, it really depends on how strict I want to be and how good of a quality I want to maintain. Some manufacturers may set a high limit based on this 2 milliamp average number of leakage current. Some manufacturers may set a high limit of 2.5, or they may actually set it at 2.1 if they're very strict. They don't want any of the products to pass if it's exhibiting any more than 2 milliamps. That's where the high limit comes in. There's different methods of setting high limit. You can set it, take the average number and do a plus 25% or plus 15% or plus minus. For the high limit, you're just going to take the plus 15 or 20% of this average number. For the low limit, you can take the minus 15%, and set that as a low limit, maybe, for example, 1.8 milliamps, 1.5. It really depends on the manufacturer how strict you are, because again, this is the requirement from the standard is, the test your product shall not break down, the insulation shall not break down. So now it's really up to your quality department to determine how strict you are and how consistent you want to be with your products, when it comes to testing. And the high limit obviously is important to catch failures that are, for products that are exceeding the limit that you've set. Low limit is also important in certain cases because, for example, if you don't set a low limit and leave it at 0, you may run a Hipot test and pass it every time, even if you messed up the connections, if you forgot to connect the return lead or the high voltage lead, or somewhere in your test setup a connection is missing. It is important to have a low limit set, because if it's set to 0, then even if it measures a very small leakage like 0.1 milliamps or microamps, it will still give you a pass, even though really you've not tested your product because something was not connected. So low limit helps in terms of ensuring that our Hipot test was indeed performed with all the connections in place. While we wait for more questions, I'd like to thank you all for joining us today. I know this took more time than expected, but I guess the topic is really broad, and we want to educate you guys with as much information as we can, and that's why there's a second webinar designed for learning more about Hipot testing, because there's, like I said, we're going to talk about 500 VA, we're going to talk about AC versus DC, we're going to talk about hot Hipot testing, we're going to talk about how to set the limits and interpret failures. We're going to give you a lot more good information on Hipot testing and make sure that you are understanding the Hipot test really well. So
all right,
yeah.
Syed, I think that's it for questions. I know Bashan is going to reach out to one person so they can discuss a little further. Other than that, I think we should be good. Thank you guys all for joining, and don't forget to join us for our next part 2 of Hipot Testing 102 on Wednesday, May 18th at 10 a.m. Central Standard Time.
All right, thanks, Allison. Once again, this is your host, Syed Abidi, signing off. Hopefully this webinar was, it provided you with lots of good information that you needed to know or learn about the Hipot test, and we hope you will join us in our upcoming webinars. Keep up with us, and you will make sure we answer all your questions. Once again, thank you for our users who are outside the U.S. Taking out time at odd times of the day to join us. Have a good day.